important concepts in linear algebra that has profound applications across various fields are eigenvalues and eigenvectors. If you have ever wondered how we can break down complex transformations, simplify matrices, or even understand quantum mechanics, eigenvalues and eigenvectors play a critical role in these processes. In this video, we are going to explore what these terms really mean, how they work, and why they matter in both theoretical and practical applications. My name is Shaunak, and you are watching this video on my channel, Physics for Students. Welcome to this video where we are going to explain eigenvalue, eigenvector, and what is an eigenstate. Now, the term itself, the word eigen itself, sounds not something which is close to English language. So what is eigen and what is the origin of the word? Let us look into that in the first part of the video. So the word eigen actually comes from the German word which means own or characteristic. If I explain further, you can tell that it is something which resembles belonging to someone themselves, not to someone else. Well, obviously you are willing to learn the mathematics of these terms, but what about telling a little bit more so that the later understanding of these concepts become better? So if you look in this German word, it actually means peculiar, strange, or unique. That means it describes something that has its own particular nature. This term Eigenschaft, pardon me for my wrong German pronunciation, this also means property, characteristic, or trait. Eigenheim, it also means own home, or it refers to a house that someone owns personally. And this German word also means independent or autonomous. It implies being self-reliant or functioning on its own. So all these four terms, Eigenschaft, Eigenheim, and the other two terms actually refers to something of their own. And from this very understanding of the or the literary understanding comes or crops up the understanding of physics and mathematics. So here we can say that overall the word eigen means own, inherent or characteristic, and it refers to something that belongs to itself. In German, eigen conveys a nature or a sense of ownership and uniqueness, and which is not shared or derived from others. So finally we can say this, for example, this word das ist ihnen eigen is a German word which means that is typical of them. Then mein Eigenhaus, house means my own house. So overall I just wanted to give you an understanding that this is typically of intrinsic, inherent, which has its own uniqueness and characteristic. So from here what we can say is this. So eigenvalue and eigenvector in mathematical terms, we can say eigenvalue and eigenvector means is reflected in how these values or vectors or characteristics of a particular transformation, and it represents something very intrinsic to the system being analyzed. As I told you that until you understand the literary meaning of that, it is very difficult to understand how the concepts do evolve. So from here, before going into the mathematics, let us look into what do eigenvalue and eigenvector mean in terms of simple words. So first we take what is called an eigenvalue. So from here we can understand that it refers to the characteristic value associated with a specific transformation, and it represents the scale. There's a scale or factor that is specific to transformation. That means it is a value, as you understand, eigenvalue. So eigen means own value. So it has got something to do with the scale or factor, which we will see what happens in transformation. And what is an eigenvector? It also refers to the characteristic vector, but it actually tells that it is a vector that represents the own or inherent direction of the transformation, and it really doesn't change. Although the magnitude may change, and we will look into which one actually denotes the change, which one remains inherent or constant. But from the German term, we can understand that it is all related to its own characteristic and something inherent. Now, before going into the mathematics, I would like to explain to you two concepts which would be very important in our understanding. First one is called what is a shear mapping. Now, in case of a shear mapping, as you can see, this blue one, once we stretch it, once we shear it, it takes a different kind of a geometrical shape. So P moves to P prime, X moves to X prime, and we get an angle which is called a psi. In order to make a better understanding, you look into this. This is a original shape, which is this kind of a square, and it goes X angle shear mapping, so it becomes a different kind of a structure, and then it goes into Y ended shear mapping or YX shear mapping, it becomes a little bit different. I mean to say, in the two dimension, it is very difficult on the computer screen to describe, but this is how it looks like. So what is the purpose? The purpose is basically to tilt or slant an object without changing its area. This is important, and it will soon become very clear in the next few minutes, because this is what we are going to look. So we are trying to tilt or slant an object without changing an area, and the effect is that changes the shape of the object but preserves its area. Now we come to the very usual, what we all know, it's called a rotation. So here is the rotation. There is a center, and which on this triangle is rotating, and you can see here there are different arrows which have changed from 36 degree to 66 degrees, and it has become 90 degrees also. So what is the purpose? So in terms of rotation, we say that it turns an object around a fixed point. There is no fixed point, remember, in shear mapping, and it preserves the shape and size of the object. Here also it preserves the shape and size of the object. So in general, now you can read that rotation, the direction of the vector changes, meaning most vectors are not eigenvectors. We'll come to later what is an eigenvector. I mean to say, because they are not eigenvectors, that means something which does not remain constant. Obviously, in case of a rotation, the vector changes. So this is because why? Because rotations alter the directions of vectors, so they no longer remain aligned with their original position. Now we are going to take first what I just talked earlier, is that we are going to take a look into what is called a shear mapping, and then we will understand that. Now here is an X and Y axis, and this is a kind of a tree. Now, if I do a shear mapping, and in the shear mapping, if I do a kind of a stretching of this one, so it goes around here. Okay. So, and I will try to show this with this red vector. Let me show it again, this one, which goes with the dotted line. And again, I would try to show you this famous one. This red arrow, which is pointing here, is the eigenvector. Right? The red arrow eigenvector changes the direction, but you see the blue arrow does not. So from here, what becomes clear, that in case of a shear mapping, the eigenvector will change, but the blue arrow, this one, the eigenvalue will change, but the blue arrow, that is the eigenvector, will remain constant. Although it tilts in this direction. Now, if I take this famous painting of Mona Lisa, you can see here also the blue arrow doesn't change, but the red arrow changes, and this is basically of the shear mapping. So the blue arrow is an eigenvector. So it is not changing of the shear mapping. It doesn't change its direction. And because its length is unchanged, it has got a value which is called an eigenvalue is 1. So if the blue arrow is an eigenvector, then that means it is not changing, the blue one, but you can see the red arrow is bending on this direction, and that bending due to the shear mapping is what is called the eigenvalue. And because it is a unit vector, or it has got a length of 1, it has got an eigenvalue which is 1. Same happens with the case of a tree. So the eigenvalue changes in this direction, but the eigenvector in the xy direction, it remains the same. So now let us take the same tree example and let us stretch it. So again, we get an eigenvector in this direction eigenvector, and this tree, now you see it stretches. And how much it stretches, that is basically registered with eigenvalue. So eigenvalue is the stretching factor, but you see the tree, if you see the eigenvector in the x and y direction, they are the constant, they remains the same. So from this example, what we can say, number one, is that the directions of the eigenvectors remain constant during the stretch. Obviously x and y doesn't change. They continue to point along the x and y axis. Obviously vector along the x axis is stretched by maybe 2, 3 ... times, it can be n times. And what we also see is the vector along the y axis stretched by ... it can be number of times. So we say that in the case of a stretching, the eigenvectors or the direction of the stretch along x and y axis remains the same. That is unchanged. And what changes are the eigenvalues. I'm so sorry if I really cannot make you understand, because in this way it is a little bit difficult. So eigenvalues tell us how much it is a value. We will see it is a scalar value which actually is stretched by a factor of whatever. And these eigenvalues represent how much the scaling factor actually takes place. Now this is the stretching which is done on a shear mapping. Now we come to the rotation part. We have already seen those vectors which have rotated, and I would like to mention this point, that eigenvectors in general rotation, the direction of vector changes, so they are not eigenvectors. In the earlier example, if you see this one, these are eigenvectors because the xy remains constant, only the scaling factor changes. But in this case of a rotation, as you can see, the entire vector itself is rotating and it is changing the direction. That means it is not remaining same. So this is because the rotations alter the direction of the vectors. So from here, if we take the same kind of a example, how the eigenvalues etc. changing. So if this changes, the dotted line, the blue one, we can say that this is denoted by lambda, and it is a scalar that represent by which factor, by which the eigenvector is stretched or compressed. And v is a vector that maintains its direction during the transformation, but may change in terms of magnitude. So this gives you a kind of a visual pictorial understanding of what is an eigenvalue, what is an eigenvector. But definitely there are certain relationships, I would say differences, or you can say as itself relationships or differences etc. also. I mean to say that is what we are going to look into the next part of the video. What are the differences or relationship between eigenvalue and eigenvector? This will clear a lot of concept. First, if I talk of the definition, then it is eigenvalue. Remember, it is a scalar and it tells that how much a vector is shrunk or stretched or so. Eigenvector, a vector that does not change direction under linear transformation, although it may get stretched or shrunk. If I talk of type, definitely it is a scalar. This is a vector because it's representing direction. It represents the magnitude of stretching and flipping, the value, and the vector, it tells the direction that remains unchanged. In mathematical terms, it is denoted by lambda, and this is denoted by v or any vector terms. Now, question is that when it is used. So eigenvalues are mostly used in order to measure the amount of stretching, etc. Eigenvectors are to find the directions in which the object does not rotate. If I talk of relationship, eigenvalue is associated with the corresponding eigenvector, and here what happens is that an eigenvector is defined by its relationship to a specific eigenvalue. Its relationship to a specific eigenvalue. Okay, and in here, in terms of interpretation of quantum physics, in order to mention the representation in terms of quantum physics, I would say this would be here, it would say represents measurable quantities like energy levels in a quantum system, and here I would say that here it represents the quantum states like the wave function of a particle in quantum mechanics. So we will look into what is the quantum mechanics part and what is the eigenvectors etc. that are being called. So it represents measurable quantities, and here it represents quantum states. If I look into the geometric interpretation, then an eigenvalue represents, obviously as we saw, how much it is stretched or shrunk, etc. An eigenvector, obviously it points to the direction which is unchanged. Talk of applications, it is used in various ways, because in linear algebra, matrix diagonalization, quantum mechanics, a lot. And eigenvectors is used to describe the behavior of a system under linear transformation and to understand the underlying data. So from all these understanding of differences and relationship, finally it boils down to this point. Eigenvalue is a kind of a how much factor, and eigenvector is a kind of a direction part. I mean to say, grossly we can say about that. Now all these are good. I mean to say, we understood by geometry, we understood by figures, we understood by a simple English language. Now the question comes, what is the eigenvalue equation and how we can actually explain the eigenvalue equation, coming up in the next part of the video. So first we will look into the eigenvalue equation as itself, and then we will try to interpret them. So this one, AV equals to lambda V, this is basically the eigenvalue equation. Now here you will see this A is basically a matrix, and it is a square matrix. Now you might ask me a question that why do we use a square matrix? We will come to that. Hold on. The V is basically the vector, and any vector is represented as an arrow. But what about if we don't represent this as an arrow, I mean to say the magnitude and direction, and we represent by this, V equals to 5 and 2. It's a kind of a matrix. And here, if I plot the matrix in a geometry, this one would represent 5, this one would represent 2. So that means this actually encodes both the size and the direction of the vector. So instead of showing it in an arrow, this is a much convenient way, isn't it? Where you can see both the size and vector and it in a matrix. Now, if I take this matrix, this V, if I take it as a square matrix, and this can be applied to a vector which is V, this actually provides another vector, for example, Y. It can be anything. So let us take an example. For example, this one, here this is the original vector and it produces a different vector, that is N9,923. Now remember that for some matrices, obviously we find some vectors that do not get transformed into one another, and that is what is the catch it is. Let us see into an example. If we take this vector and then we do a kind of a what we do is the matrix multiplication, and what we get around is here, and if I assign the values, this one as A and this one as B, you will see both of them are the same. So here also we get 5 and 2, here also we get 5 and 2. So from here what we can deduce is that, and this is denoted by lambda, that the same vector B is actually stretched or scaled by lambda B factor. So here you can see the other equation, it was 923, and here it is stretching, it is the same vector which is a little bit stretched. So what we say from here is that the stretch vector is known as the eigenvalue of the matrix A, because the value is what? The stretching factor, and that is what it is stretched. So from here we can say that we found the eigenvector of this matrix, and B is basically the stretch factor is an eigenvector of the matrix A, and that is why we say that we found what is called an eigenvalue equation. Now, the mathematical equations of eigenvalue and eigenvector can be explained a little bit in more details. In this part of the video, we are going to look a little bit more into understanding how these equations actually perform and do they change. So, the fundamental equation that defines eigenvalues and eigenvectors we have already seen is this. Now, this is what is called a square matrix. I will answer to this question, why it is square, why it is not. And this is basically the eigenvalue. And this one to this one is basically the eigenvector. So actually this equation tells a lot of important relationships. What it tells, first of all, it is essentially describes how linear transformations happens and what are its results. And always we understand that linear algebra is basically of linear transformation, and this linear transformation I would say transformations are extended into quantum mechanics, because nature, as we see, inherently is linear in case of quantum physics. So here we see that if you do a kind of a linear transformation of a matrix, which is when applied onto a vector which is V, then what we can say, it can be either compressed, it can be rotated, it can be stretched, or it can be flipped. So the vector V is applied, is special because it applies to eigenvector, and this means that the transformation of A is applied to V, the direction of V remains unchanged, the transformation only scales rather than rotating or otherwise distorting. So the scalar lambda is the eigenvalue, and how it actually changes. Now here you see this lambda is greater than 1, it is stretched. If lambda 0 is less than 1, we can say it is compressed. If lambda is equal to 1, it remains unchanged. If lambda equals to 0, then it is the original position. Lambda less than 0, then V or the vector is, I would say, the value is flipped, and it reverses in the direction. So that is why, this is special, because all these cases you can see that it tells how much the eigenvector v is scaled or stretched or compressed or flipped or whatever it happens when the transformation of this matrix is applied on the vector. And these actually carries different values which I have shown. Let me demonstrate you with a very simple example. For example, this one, if I apply it over this, then what happens? We get this one. And here you can see lambda equals to 2 because it is stretched by a factor of 2, which is the eigenvalue. And thus we infer that the direction of the vector v remains the same, but its length has been doubled. So from here we will now try to see that if AV equals to lambda v in terms of mathematics, I mean to say using the equations, can we do that? So here you can see if I take this matrix, then an eigenvector is, and the eigenvector is 1, 4 with a matching eigenvalue of 6. Then once we perform what is called a matrix multiplication, you all know that we get something like this. And lambda v actually gives us 624. So this 614, which ultimately returns to 624. So what do we get from here? You see these two are the same. These two are absolutely the same, and it gives us a wonderful proof that AV equals to lambda v. So just doing the matrix multiplication, we get that. Now the question arises that how do we find the eigenvalue and eigenvector? I mean to say mathematically, how do we find that? So we start by finding the eigenvalue, and we know that the equation that we have saw, that AV equals to delta V. So the first step is that we have to put an identity matrix AV equals to lambda IV. Now bringing it on the left hand side, what we get is equals to 0. And if V is non-zero, then we can hopefully solve delta V and we get a determinant which is 0. Okay, so here is a kind of a simple illustration which will actually show you this. So we will start with this, the same one which you have seen, minus 6, 3, 4 and 5, which will be, we need to solve this for lambda. So we will start with A minus lambda I, which is the identity matrix, which equals to 0. Turning to the next page, if we do this calculation, it equals to 0, which will finally give this equals to 0. And then we will calculate the determinant, which you can do later in your homework page. This is 0. And this would give us a simplified quadratic equation, which is this. And if you solve this quadratic equation, using this, you substitute the value, you will get lambda equals to minus 7, and you also get lambda equals to 6. So that means there are two possible eigenvalues, yes, and that is 2. So now that we know the eigenvalues, that is minus 7 and 6, let us see how we can find the eigenvector. So first the eigenvalue and then the eigenvector. So we will start with lambda equals to 6. We will substitute this into the value. If you put the values, we will get into this. After multiplying these two equations, we get into this. Bringing to the left hand side, a little bit sorting will give us this. Now here what happens, either of these equations will equal to y equal to 4x as the eigenvector in any non-zero multiple of this. So the eigenvector of non-zero multiple of this 1, 4, and we get the solution which we have done is this one, the same one, 624. We have done this. And also if you turn the page in a fresh page, we do this, 661 equals to 624. And finally again this 624, if you can go back here, you will see this one is 624. The next page is also 624. So from here we prove that AV equals to lambda V. And obviously you can, we started with what? We started with, starting with 6, right? So we actually started with the value of 6. Now what you can do is that you can start solving it for minus 7. The same way, the same technique. The same technique, instead of lambda equals to 6, you can put in lambda equals to minus 7. And you can let me know in the comment box how your equation looks like. Now eigenvectors, remember, also works perfectly in what is called a 3-dimension. In 3-dimension, 3 by 3 matrix, etc. Again, we are going to the square matrix. So let us look at a simple example of eigenvectors in 3 dimensions. The first one is that how to find eigenvector for this matrix, this one. So simple. First we calculate with the identity matrix A minus lambda I, which I have skipped over here. I should have written, but this gives us to this value. And now if we calculate, the determinant should be equal to 0. And then we calculate further this, and this ends up actually into a cubic equation. If you calculate this, this will end up a cubic equation. But just looking at it, you can say that one of the roots of 2, because of 2 minus lambda, and the part inside the square of bracket is a quadratic equation. So the eigenvalues will be lambda equals to either minus 1 or plus 2 and 8. And so you need to solve this equation. So the value would be 1. So let us start again with lambda equals to minus 1. And with this, how do we proceed? So from here we turn to the next page and we put the value minus 1. After multiplying, what we get is this one. Now we bring everything to the left hand side, and what we get is this. So x equals to 0 and y equals to minus z. So the eigenvector of non-zero multiple will give into this. And now if we test AV, because we have to test two things, right? AV and lambda V. If we test AV, then the equation gives this. And if we test delta V, the equation gives this. That is how we get. Now you can also try out. So from here what we get again, 0 minus 1 1, 0 minus 1 1, and I put a blue tick because this is something which again shows it is the same. And you can try out for either other eigenvalues 2 and 8, and you can let me know in the comment box. Now this is also applicable with the equation of rotation. So what is rotation? Let us say that we actually calculate the matrix will do a rotation by theta, and the values will be cos theta minus sin theta cos theta. And if we rotate, for example, I'm just taking for example 30 degrees for the convenience. Rotate by 30 degrees will give us square root of 3 by 2, and sin 30 will give us 1/2, right? And then once we put these values over here, what we get is this. Now let us imagine this to be an xy coordinate, and if I take any letter f and if I rotate it in this all the direction, that means I am taking all the points and rotating it something like this. So if we rotate all the points, what is the direction that does not change the direction? I mean to say this is wrong English, but it actually makes sense. So what is actually the direction that does not make the direction? Let us go ahead and do a simple calculation, and let us find out our results. So here we again start with this one. So what we are doing again, I am calculating a minus lambda I. So here we get the value which is this one, and the determinant should be equal to 0. So which gives us an equation like this, and again it will result into a quadratic equation like this. And the roots are again, it is coming to what is called an complex. The eigenvalues will be complex. Obviously the eigenvalues would be complex. So from here what we can tell you is that what is the eigenvector that matches with this? I mean to say square root of 3 by 2 plus minus I upon 2. Let us try with this, and what we find is that so earlier what we have looked upon with this part. Now we are looking upon AV equals to lambda V. So if we take AV equals to lambda V and we put what are the values which are known, and if we multiply this equation, it will result into this and into this, and which will simplify if you do it mathematically. X equals to IY and minus Y equals to IX. And the solution is any non-zero multiple, so it would result into I1 or it would result into minus I1. Now here is a question. This is done with 30 degrees, right? Now the question is that will it be applicable for anything which is other than 30 degrees? For example 40, 45, 60, etc. That you can really work out and let me know in the comment box. But this actually shows how the rotation and how the AV equals to delta V and how things happen. Now we come to the central and the most important part of our video, which is the eigenvalues and eigenvector in quantum physics. Because in quantum physics this is definitely used, not only that, in various other ways. So we will look into the usage of eigenvalue and eigenvector in quantum physics into the next part of the video. Now before I go ahead, I would like to tell you that in quantum physics, remember, physical observables such as energy, momentum, position are represented by operators. So here you can see this is an energy energy, which is denoted by the Hamiltonian operator, which actually represents the total energy of the system. In many quantum systems, especially of particles and fields, they are expressed as this, where P square is the kinetic energy operator, which is a square of the momentum operator, and Vx is the potential energy, which is a function of position. We can also say that this Newtonian, it's a diagram. What is this? This is momentum, and this is a momentum operator. And the momentum operator is basically denoted by this differential operator, where P hat is actually the momentum operator, I is obviously the imaginary unit, H bar is the reduced Planck's constant, and d by dx is basically the derivative with respect to its position. We can also get something like this. This is the position operator. So what is the position operator? Corresponds to the particle, position of a particle in the position basis. This operator is simply multiplied by the position variable, which is this. X hat is the position operator. Psi x is the wave function depending on the position of x and whatever it is. Now all these operators, the energy, the momentum and the position, they actually define what is called a quantum state. What is a quantum state? It is a kind of a description of the condition. So quantum state can be actually represented in two ways. First is using the psi x, and another is the Dirac equation. That is the Bra and the Ket. So now the question is that in simple terms, we know that quantum state is what? That represents where the particle might be found, its momentum, its energy and so on. Now, one way to represent a quantum state is the wave function or the Dirac equation. Now, here is something important. Now, if I take this equation, O hat psi equals to lambda psi. Now, what does this mean? This actually is the operator. This one is the eigenstate. This one is the eigenvalue. And this one, we have already stated, is the eigenstate. So, when an observable operator, whatever is observed, whatever we are observing, it acts on a quantum state, which is, I told, which finds out the particle is in where, momentum, etc. The result can be actually described by what is called an eigenvalue equation. So this is how actually quantum mechanics operates. So we use this and we describe the on an operator used on this, which gives an eigenvalue equation. So we try to revisit this one. So here you see this lambda. It represents the measured value. That means what we are seeing physically, physical quantity. And if I try to measure, for example, the energy, then this lambda would be the energy that you observed. And this is actually based on the measurements. So the physical observables are represented by operators, which is the O hat. And the operator acts on this and state, it simply multiplies the state by a constant lambda from the state psi. Or it can be the Dirac equation. It's called an eigenstate of the operator corresponding to the eigenvalue. And from here you can see this psi actually represents a quantum state. We have already defined what is a quantum state. And when we measure, the quantum state collapses. And it collapses where? To any one of the eigenstates of the operator corresponding to what is called the observable. Or what is called the observable. So from here what we can deduce is this one. An eigenstate is special. Why? Because if the system is in this state, the measurement of the observable will yield the eigenvalue in that state with certainty. That means there is absolutely no doubt on that. And what we get is that if the system is already in an eigenstate of the observable, the measurement will yield the eigenvalue associated with that eigenstate with certainty. Certainty means there is no ambiguity. There is nothing which will at all create any doubt or whatsoever. Let us look into that, and I will try to demonstrate this with a particular example. Now in this example, what I'm going to do is that I'm going to take a kind of a quantum system. For example, I just drew this. This is a kind of a quantum system. Now I would denote this with the Hamiltonian H bar, which is basically what we called is the energy operator. We called it an energy operator. So from here, what I would say that consider that there is a particle. This is a particle, okay? A particle in a quantum system where energy is observable, represented by the Hamiltonian operator H bar. And suppose the particle is in an eigenstate of energy, which I'm again denoting by Dirac notation, En, where this one is equal to this one. And what is this? This vertical bar En is the eigenstate of the Hamiltonian energy operator. This one is eigenstate of the Hamiltonian energy operator, and En is eigenvalue, and this eigenvalue corresponds to the specific energy value. So from here what we can say, that if you measure the energy of the particle of this eigenstate, which is right there on the screen, the result will always be this with 100% certainty. That means there is no chance of getting any other energy value. That is, with certain that if you measure the energy of the particle where it is in the eigenstate En, the result will always be En with 100% certainty, and there is no chance in the world that you are going to get an energy value. However, we should remember that quantum states are in a superposition. And if the system is in a superposition like this, then where E1 and E2 are eigenstate with values of what? E1 and E2 without the bars, and C1 and C2 are the constants, which I have not written over here, then measuring the energy will give E1 and E2, and this would be determined by the probability of this one. And what is this probability? This is just squaring the amplitude, which is the Bond's rule. So result is here in case of a superposition. Remember, it is not certain, unlike the case when the system is in a single eigenstate. So the earlier example shows that the system is in a single eigenstate. Here there is a superposition, so you cannot say that the result of the energy will be 100% certain. The same thing can be well demonstrated very easily using a Schrodinger equation. So if I say the time independent Schrodinger equation is this, then what we see is that this is the Hamiltonian operator, which represents the total energy of the system, kinetic plus potential. Then this one is the wave function of the particle, which depends on the position in the case of one-dimensional system. And this one is the eigenvalue, that is the energy eigenvalue, which corresponds to the measurable energy of the system. So if I again take this kind of a system which is denoted by psi, and this would be energy which always be equal to E. When measurement of energy is made, the result will always be the eigenvalue E. The system will always remain in the state psi. And what we can say is that the equation actually tells us that when the Hamiltonian operator acts on the wave function, it returns the same, I would say, wave function multiplied by a constant E, which is the eigenvalue corresponding to the observable, in this case energy, but you can take other values also. So let us draw a fresh page where we can say the same thing a little bit clearer. This part is the eigenvalue, which is the energy. This part is the eigenstate of the Hamiltonian operator. You can take X, you can ignore this, but doesn't matter. This is H, the Hamiltonian energy operator. So for a given wave function eigenstate, the energy of the system precisely E, and it is a measurable quantity. So the wave function actually describes the system state, including the probabilities where a particle might find. So here if I take this kind of a quantum system denoted by the energy and psi x, then again we can say that energy will always be equal to E with 100% certainty. If we do the calculations, and if we take a kind of a system which is one dimensional, and it will precisely yield into the value E. Now another thing which actually is also important is called the electron spin, and this spin is very much I would say measured using eigenstate and eigenvalues, which I will be covering in the next part of the video. And I will also explain that why quantum physics uses eigenstate and I would say eigenvalue and eigenvector, and what is the advantage, how things or life becomes so easy using eigenvalue and eigenvector in quantum mechanics, along with the electron spin, in the next part of the video. So that's all for today's video. I am immensely thankful for those who have taken up time for watching. Please do subscribe to my channel Physics for Students by clicking on the bell icon and get all the notification from Physics for Students. You can write to me at this email ID, and you can like and subscribe to my other channel, General Relativity Explained, where I put up mostly videos on general theory of relativity. You can follow me also on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be back with more videos, and the second part of eigenvalue and eigenvector will continue, but please do let me know your reactions. How do you like and how do you enjoy watching this video in the comment box? We'll be soon back, but till then, goodbye.